Good day. We're going to discuss the diagonalization and the definition and how to solve the problem. So the definition is the conversion of a matrix into diagonal form is called diagonalization. The eigenvalues of a matrix are clearly represented by diagonal matrices. A diagonal matrix is a square matrix in which all of the elements are zero except definition, process, and solve.
Example 1. Diagonalize a matrix. Let 2, 0, 0, 1, 4, negative 1, negative 2, negative 4, and 4. Find an invertible matrix P and diagonal matrix D such that P is equals to 1, AP equals to D. Solution. By theorem 7, 2, 2, we use the eigenvector of A as the column of P and the corresponding eigenvalues of A as the diagonal entries of D. First, we will find the eigenvalue of A. To do so, we solve D A is 1, E equals 0 as follows. This computation is left as an exercise and you should verify that the eigenvalues are eigenvalues T is equals to 2, eigenvalues 2 is equals to 2, and eigenvalues 3 is equal to 6. Next, we need to find the eigenvalues. We first find the eigenvectors for A sub 1, eigenvalues 2, solving where Ts are scalars. Hence, there are two basic eigenvectors which are given by diagonalize a matrix. You can verify that the basic eigenvector for that we construct the matrix phi as follows. That is the column of phi are the basic eigenvectors of A, then you can verify that. You can see that the result here is diagonal matrix where the entries on the main diagonal are the significant values of A were expected is based on theorem 7.2222. Notice that eigenvalues on the main diagonal must be in the same order as the corresponding eigenvalues in P.
Good morning, ma'am. This is the part of my report. Part 2, diagonalization of examples. Example number 1, diagonalize a matrix. Find an invertible P and the diagonal matrix D such that P minus 1 AP equals D. Solution by theorem 7.2.2 use and use of A as the column of P and the corresponding of A as diagonal entries of D. First, we'll find the A. To do so, we solve 0 as follows. These are the samples. DET, column 1, 0, 0, next column 0, 1, 0, third column 0, 0, 1. The computation is in the left exercise and you should verify that eigenvalues are A1 equals 2 equals 2 and 3 equals 6. Next, we do find the eigenvectors. We first find the eigenvectors for 2 equals to solving x equals 0. To find the eigenvectors, we find that the eigenvectors are t negative 2, 1, 0 plus is 1, 0, 1, where t is our scalars. Hence, there are two basic eigenvectors which are givenly x1 negative 2, 1, 0 times x2 equals 1, 0, 1.
Sample 1, diagonalized matrix 2, 0, 0, 1, 4, negative 1, negative 2, negative 4, 4. Find an invertible matrix P and a diagonal matrix D such that PEPD. Solution by Theorem 7.2.2. We use the eigenvectors of A as the columns of P and the corresponding eigenvalues of A as the diagonal entries of D. We will find an eigenvalues of A. To do so, we solve as follows: 1, 0, 0, 0, 1, 0, 0, 0, 1, negative dash 2, 0, 0, 1, 4, negative 1, negative 2, negative 4, 4. This computation is left as an exercise and you should verify that the eigenvalues are. Next, we need to find the eigenvectors. We first find the eigenvectors for solving.
This is example of a matrix which cannot be diagonalized. Let A 1, 1, 0, 1. If possible, find the invertible matrix P and diagonal matrix D so that P minus 1 EP equals D. Solution. Through the usual procedure, we find that the eigenvalues of are eigenvectors 1 equals 1, eigenvectors 2 equals 1. To find the eigenvectors, we solve the equation eigenvectors 1 minus A x equals 0. The matrix eigenvector 1 minus A is given by eigenvectors minus 1, negative 1, 0, eigenvector negative 1. Substituting in eigenvector 1, we have the matrix 1 minus 1, negative 1, 0, 1, minus 1 equals 0, negative 1, 0, 0. Then solving the equation, eigenvector 1 minus A x equals 0 involves carrying the argumented matrix to its reduced row echelon form. 0, negative 1, 0, 0 equals 0, 0. To 0, negative 1, 0, 0, 0, 0. Then the eigenvectors are of the form T 1, 0. And the basic eigenvector is x sub 1 equals 1, 0. In this case, the matrix A has one eigenvalue of multiplicity 2, but the only basic eigenvector, in order to diagonalize, we need to construct an invertible 2 by 2 matrix P. However, because only has one basic basic eigenvector, we cannot construct this P. Notice that if we were to use x sub 1 as both columns of P, P would P would not be invertible. For this reason, we cannot repeat eigenvectors in P. Hence, this matrix cannot be diagonalized. Thank you.
Example number 2. A matrix which cannot be diagonalized. Let A is equal to matrix row 1, 1, 1, row 2, 0, 1. If possible, find a invertible matrix P and diagonals matrix D so that P minus A 1 AP is equal to D. So solution. Through the usual procedure, we find the equivalent eigenvalues of A are lambda 1 is equal to 1, lambda 2 is equal to 1. To find eigenvectors, we solve the equation parenthesis lambda 1 minus A parenthesis multiplied by X is equal to D. The matrix lambda 1 minus A is given by matrix lambda 1 row 1 negative 1 row 2 0 lambda negative 1. So substituting it in, lambda 1 is equal to 1. We have the matrix 1 minus 1 negative 1 0 1 negative 1 is equal to 2 by 2 matrix row 1 0 negative 1 row 2 0 0. Then solving the equation lambda 1 minus A multiplied by X is equal to D involves carrying the following augmented matrix to its reduced row echelon form. So matrix row 1 0 negative 1 row 2 0 0 and the eigenvalues is 0 0. So then the eigenvectors are the form T 1 by 2 matrix 1 and 0, and the basic eigenvector is x sub 1 is equal to matrix row 1 1 and row 2 0. In this case, the matrix A has eigenvalue of multiplicity 2 but only the basic eigenvector. In order to diagonalize A, we need construct an invertible 2 by 2 matrix P. However, because A has only one basic eigenvector, we cannot construct this P. Notice that if we were to use x1 as both columns of P, P would not be invertible. For this reason, we cannot repeat eigenvector in P. Hence, this matrix cannot be diagonalized.
A matrix cannot be diagonalized. If possible, find the invertible matrix P and diagonal matrix D so that P1 A P equal to D. Through the unusual procedure, we find that the values of A to find the eigenvectors, we solve the equation. The matrix is given by subtracting. We have the matrix. Then solving the equation involves carrying the following augmented matrix to its reduced row form. Then the engine vectors are the of the form of the basic engine vectors is x1 equal to
Good morning, ma'am. This is my part of my report. Sample number 3. A real matrix with complex eigenvalues. Find the eigenvalues and the eigenvectors of A. Solution. We will first find the eigenvalues as usual by solving the following equation. First column. Sample first column. 1 0 0, second column 0 1 0, third column 0 0 1, and the second row of column 1 0 0, and the second 0 2 1, third column is 0 negative 1 2, and close parenthesis equals 0. The reduce to open parenthesis lambda and minus 1 and close parenthesis by multiply and open parenthesis lambda 2 minus 4 and plus 5 and close parenthesis equals 0 point. The solution are lambda 1 equals 1 and lambda 2 equals 2 plus I. There is nothing new about finding the eigenvectors. For lambda 1 equals 1. So this is the left of the list as an exercise. As usual, we solve the equation open parenthesis lambda 1 minus a and close parenthesis x equals 0 as given by open parenthesis 2 plus I close parenthesis and sample of column 1 0 0 0 1 0 and third 0 1 0 0 1 and the second column is 1 0 0 and 0 2 1 and third column 0 negative 1 and 2 x and third column in parenthesis 2 plus I and close parenthesis. First column 1 0 0 and 0 1 0 and 0 0 1 and the second column is 1 0 0 and 2 0 1 and 0 negative 1 2 x equals 0 0 0. In other words, we need to solve the system represented by the augmented matrix. Sample of column 1 plus I and 0 0. Second column 0 I and negative 1. Third column 0 1 I and 0 0 0. We know use our row operation to solve the system. Divide first row by open parenthesis 1 plus I and close parenthesis and then take minus I times the second row and to the third row. This yields example of column. First column 1 0 0 and 0 I 0 and 0 1 0 equals 0 0 0. Now multiply the second row by minus I to obtain the reduced row echelon form by column. Open parenthesis 100 and 010 and third 0 negative I 0 and 000. Therefore, the eigenvectors are the form. Example, T and open parenthesis 0 I and 1 and close parenthesis. And the basic eigenvectors is given by x2 equals open parenthesis 0 I 1 and close parenthesis. Hence, the basic eigenvectors is given by x3 equals 0 negative I 1. To verify, we check that ex3 equals open parenthesis 2 minus I and close parenthesis x3 as follow. Example, column 1, 1, 0, 0 and 0, 2, 1 and 0, negative 1, 2 and equals 0 and negative I and 1 equals third column is 0, negative 1 and 2 and we check that ex3 equals open parenthesis 2 minus I and close parenthesis x3 as follows. Sample example of column 1 0 0 0 to 1 and 0 equal 0 minus 1 and 2 and followed by 0 0 and negative minus I and 1 equals negative 1 and negative 2I and 2 minus I equals open parenthesis 2 minus I and close parenthesis and 0 minus I and 1. That's all. Thank you.
Example 4. 2 by 2 matrix diagonalization. Case lambda is equal to negative 2. In this case, the eigenvector x satisfies. Ax is equal to negative 2x. Let x be. X is equal to opening square bracket x1 and x squared close square bracket. We have opening square bracket 1, 3 and 4, 2 close square bracket times opening square bracket x1 and x squared close square bracket is equal to negative 2 opening square bracket x1 and x2 close square bracket. Rearranging this equation, we obtain x1 is equal to negative x2. Therefore, the eigenvector is expressed as x is equal to x squared opening square bracket negative 1 and 1 close square bracket, where x2 is an arbitrary value. We set x2 is equal to 1 for convenience and obtain x is equal to opening square bracket negative 1 and 1 close square bracket. Invertible matrix P by 1.4 times 1.4 and 1.5 times 1.5. We obtain the invertible matrix PP as P is equal to opening square bracket 3/4 -1 and 1 1 close square bracket.
Stephanie Ibrano, and this topic is 2x2 matrix diagonalization. Example number 1. Let A be a 2x2 matrix defined as A minus 1 and 4, 3 and 2. Diagonalize A and find the invertible matrix to diagonalize A. For a square matrix A, matrix diagonalization is to find a diagonal matrix A satisfying P to the power of -1 AP is equal to A, where P is an invertible matrix which diagonalize A. In the following, we find the diagonal matrix A for the matrix A in 1 and 1, and the invertible matrix P that diagonalizes A. It is known that the diagonal elements of a diagonalized matrix are the eigenvalues of the original matrix. Therefore, by obtaining eigenvalues of A and arranging them in diagonal elements, diagonalized matrix A is obtained. Deviation of diagonal matrix A. In order to obtain the eigenvalue A of A, we need to solve the characteristics equation, which is a polynomial equation in the variable or eigenvalue m, since the left-hand side is a 2 times 22 times 2 determinant. Then the solution of 1 and 2 and 1 and 2 are x is equals to 5 and -2. By arranging the solution in diagonal elements, we obtain the diagonalized matrix A as A is equals to 5 and 0 and 0 and -2. Derivation of invertible matrix that diagonalize A. The invertible matrix PP diagonalizing the matrix AA. AA is the matrix whose column vectors are the eigenvectors of AA. Therefore, PP is obtained if the eigenvector for each eigenvalue of AA is obtained. So we will derive the eigenvectors of eigenvalues of AA as follows. Case A is equals to 5. In this case, the eigenvectors x satisfies AX is equals 5x. Let x be x is equals to x sub 1 and x sub 2. We have 1 and 4, 3 and 2 times x sub 1, x sub 2 is equals 5, x sub 1, x sub 2. Rearranging this equation, we obtain x sub 1 is equals 3/4 x sub 2. Therefore, the eigenvectors is expressed as x is equals to x sub 2, 3/4 and 1. Where x and x2 is an arbitrary value, we set x2 is equals 1 for convenience and obtain x is equals 3/4 and 1. Case A is equals -2. In this case, the eigenvectors x satisfies AX equals -2x. Let x be x is equals to x sub 1 and x sub 2. We have 1/4 and 3/2 x sub 1 x sub 2 is equals -2 x sub 1 x sub 2. Rearranging this equation, we obtain x sub 1 is equals x sub 2. Therefore, the eigenvectors is expressed as x is equals x sub 2 and -1/1. Where x2 is an arbitrary value, we set x2 is equals 1 for convenience and obtain x is equals -1/1. Invertible matrix P by 1 and 4, 1 and 4, and 1 and 5, and 1 and 5. We obtain the invertible matrix PP as P is equals 3/4/1 and -1/1.
Good afternoon, everyone.
diagonalization, the conversion of matrix into diagonal form is called diagonalization. The eigenvalues of a matrix are clearly represented by diagonal matrices. A diagonal matrix is a square matrix in which all the elements are zero except the principal diagonal elements. Example: find the characteristic of a polynomial. The characteristic of polynomial p of t of a is pt equals determinant e minus ti equals 4 minus 4t negative 3 negative 3 3 negative 2 negative t 3 negative 3 1 negative 1 1 2 2t. Using the cofactor expansion, we get qt equals to negative times t minus 1 squared times t minus 2. Step 2. Find the eigenvalues. From the characteristic polynomial obtained in step 1, we see the eigenvalues are lambda equals 1 with algebraic multiplicity 2 and lambda equals 2 with algebraic multiplicity 1. Step 3. Find the eigenspace. Let us first find the eigen e sub 1 corresponding to eigenvalue lambda equals to 1. By definition of e sub 1 is the null space of matrix. E minus I equals 3, negative 3, negative 3, 3, negative 3, negative 3, negative 1, 1, 1. With the matrix 1, 1, 1, negative 1, negative 1, and 0, and so on. By elementary row operation, hence if a minus I equals to x equals 0 for x, we have x sub 1 equals x sub 2 plus x sub 3. Therefore, we have e sub 1 equals n times a minus I equals to x er and x equals to x sub 2 with the matrix 1, 1, 0. Step 4. Determine linear independent eigenvectors. From step 3, the vectors are b sub 1, 1, 1, 1, b sub 2 equals 1, 0, 1, b sub 3 equals 3, negative 3, negative 3, and 1 are linearly independent eigenvectors. Step 5. Define the invertible matrix S. Determine the matrix S equals to b sub 1, b sub 2, b sub 3. Thus, we have S equals 1, 1, 3, negative 3, 1, 0, negative 3, 0, 1, 1. And the matrix X is non-singular since the column vectors are linearly independent. Step 6. Define the diagonal matrix D. Define the diagonal matrix D equals to 1, 0, 0, 0, 1, 0, 0, 0, 2. Note that 1 and 1 negative entry of D is 1 because the first vectors are mainly independent. Step 6. Step 6. Define A vectors. Alright. D equals to 1, 0, 0, 1, 0, 1, 0, 0, 0, 2. Note that one column vector V sub 1 is of S is eigenspace. E sub 1 that is V sub 1 is an eigenvector corresponding to eigenvalue lambda equals 1. Similarly, the 2 and 2 in entry of D is 1 because the second column B sub 1 101 is in E sub 1. The 3 entry of D is 2 because the third column vectors B sub 3 is negative 3 negative 3 1 of is in E sub 2. The order you arrange the vector B sub 1, B sub 2, B sub 3 to form is does not matter, but once you made is then the order of diagonal entries is determined by is, that is the order of eigenvectors is. Step 7. Finish the diagonalization. Finally, we can diagonalize the matrix E as S to the power of negative 1 ES equals D, where S is equals to 1, 1, negative 3, 1, 0, negative 3, 0, 1, 1, and D is equals to 1, 0, 2, 0, 1, 0, 0, 0, 2. Here you don't have to find the inverse matrix S to the power of negative 1 unless you are asked to do so. That's all. Thank you.